Good afternoon, welcome back to the workbench. Today I want to do a video on this device here that I've recently built a couple of days ago. It's called a dim bulb tester, or at least that's, I believe, what it's usually called. There may be other names for it, I'm not sure, but I can't remember what they are, if they exist. So I'll just call it that. Anyway, it's a sort of a piece of test equipment, I guess. It can be used in a couple of different ways. Basically it's a current limiting device, and as its name implies, dim bulb tester, it uses a light bulb, and you can see that's this one here. This is a 60 watt one here. It's a standard incandescent one, and that's important. It has to be an incandescent light bulb. You can use a standard old style one like this, or you can use a halogen bulb. The whole point is it has to be a filament light bulb. With a standard filament, cannot be an LED or a CFL or a fluorescent tube of any kind, or any other thing like that. It has to be a plain light bulb. The reason for that is the properties of the light bulb and the way it works. The filament has a positive temperature coefficient to it, basically, and as it heats up, the resistance increases. So when these are cold, as is like now when it's turned off, it's at room temperature, the resistance will be quite low. I'm not sure exactly how low, maybe tens of ohms, hundreds of ohms, I don't know, quite low anyway. May even be in the single digits, I'm not sure. The point is, when this heats up, as current flows through it, it'll heat up, and as it heats up, the resistance increases. The resistance may go up to, I don't know, 5,000 ohms, maybe more, I'm not sure exactly. It's all got to depend on the wattage, obviously. Higher wattage bulbs will have a lower operating resistance because they'll use more current. Well, not because they'll use more current, but that's how they end up using more current, because their resistance is lower. And yeah, lower wattage bulbs will have higher resistance, so they use less current. But the point is, that's the change in resistance is what makes this work for this device here. And like I said, it's for limiting current. And I've got this connected to the mains, obviously. We've got the mains cords here coming in. This power goes in. That's the power out to the device I want to test. And of course, this doesn't have to be mains. It could be anything, really. You could use 12 volt, 24 volt. It could be DC or AC. It really doesn't matter. As long as the bulb is rated for whatever you're using it on. The bulb has to be matched with whatever it is. I mean, for example, here's a 12 volt bulb from a car. This is, I don't know, what does it say here? 23 watts. So I mean, yeah, if you had a 12 volt circuit, you wanted to limit the current to whatever 23 watts equivalent is. I can't figure that out in my head right now. But yeah, you could use this bulb, for example, in series with the device, and that's the thing. This has to be in series with it. So basically, all the current to the device you're testing goes through the light bulb first, and then to the device, and it can only go as high as whatever this runs at. So this is 60 watts. It'll run at whatever current it runs at. You can't really pull more current through it because just once that filament heats up to its operating temperature, no more current can flow through, so it'll just limit to whatever this is. So you want more current, put in a bigger light bulb. Want less current, put in a smaller one. It's pretty simple, and it's pretty useful. I mean, it sounds like a pretty simple thing, but you can actually do quite a lot with it if you know how to do it. But yeah, first of all, it's useful as a safety feature. Not really safety to you, or me, or whatever, but safety to the device you're testing, in the sense that you're less likely to blow something up if there's a significant fault, especially on mains. I mean, that's usually where people use them, is on a mains circuit, because that's where a lot of power is available, a lot of current capacity is available, and things can blow up and get expensive. So if you've bought some second-hand thing, and this is quite common in I think vintage radio, vintage TV, that kind of thing. It's maybe, I think, where this concept actually came from. Testing old valve radios, old tube radios, for example. The electrolytic capacitors in those often go short circuit, especially if they're like 50, 60 years old or something. Or the rectifier, if it's got a selenium rectifier, something like that. The old style ones, they can go short circuit. Well, actually I think those ones start going open circuit. Like, I think they go in high resistance as they age, but I'm not sure. Anyway, the point is, if there's some fault, especially something old that's been sitting around for a long time, you can get things have deteriorated over time, and if you apply full mains voltage and basically unlimited current to the thing, then it can blow up if there's something wrong with it, and especially with old valve equipment, you're liable to burn out the transformer, the power transformer, if you have a shorted device, shorted capacitor or something in there. So yeah, it's good to use something like this, and you can avoid potential issues. And the same can be done with repairing things. For example, I've got some power supplies here, so I'm going to use as a demonstration and show you how this thing can be useful as a diagnostic tool as well. But say I've got this computer power supply here, okay, this one is faulty, I know that for a fact. We can't say exactly what is faulty with it because I don't know yet, but say I was halfway fixing this, I didn't know exactly what was wrong with it, I changed some parts and I wasn't sure if I'd changed everything that was bad. If I plugged this straight into mains, it might work fine, I might have got everything, it might be perfectly okay. If I messed something up, if I soldered something wrong, if I got, say, a diode backwards or something, or if I created an accidental short circuit with a solder blob, or there was just extra faults that I hadn't picked up on yet, I'm plugging this directly into the mains, potentially you just blow everything up again, or cause even more damage than before, which is not a good thing. You waste parts, you waste money, you potentially cause more problems, and maybe even make the thing unfixable. If it was fixable before, and then maybe you blow something up and it's even worse, and then it's like, yeah, well, what's the point? So good to use something like this with that, and you can tell if you've made a mistake or if something else needs testing. And in fact, you can see on a previous video I was repairing a power supply that seemed to have been struck by lightning or a power surge or something. And I actually, I missed that the bridge rectifier was shorted, and that should have been completely obvious to me. Given the extent of the rest of the damage to the supply, I should have thought, yeah, that's probably going to be bad too. But I missed it, didn't think of it. Luckily I had one of these hooked up. So I've got my power here and plug it in. Well, that's not good. That lights very brightly. So we can see there's still a problem. Now what is most likely with that is probably the bridge rectifier, because I forgot to check that. So there we go. I completely forgot to check the bridge rectifier because I just assumed for some silly reason that it was fine, but hey, dead short. But yeah, I've just built this version here in a box, so it's more useful and easier to use, and we've got an actual switch on it, so I can do all that and a fuse, and yeah, it's not necessarily necessary, but it adds some extra stuff. The fuse is not obviously usually necessary because, again, the light bulb will limit the current, but I've got a switch over here which is to bypass it, bypass the light bulb. So if I'm testing something and it seems to check out okay with a light bulb on series, I can switch over to this switch and it'll give me full current availability. And then if I got that wrong and there was something really bad, then this fuse can blow if there's a severe issue. So there's that too. But back to the point. So the 2 points here, like I said, testing old equipment that hasn't been powered up for a long time, or testing something that's unknown condition. You might have bought something second hand, like this power supply, for example. You don't know what's wrong with it. Could be anything. Useful to plug something like this in, and also, again, if you're making a mistake while repairing something, it's also useful as that. And the third thing, though, which I find kind of the most interesting, is the ability to use this as a diagnostic tool. And I'm saying that in the sense that even though it's a very simple thing, a light bulb, you can actually get some decent information off this that can actually speed up your troubleshooting of something, potentially quite quickly and significantly, and help you sort of narrow down whether something is a problem in a primary side or secondary side, or something like that. It's not going to be incredibly accurate, or it's not going to magically tell you the answer or something, but it can actually be quite a lot of help, and it's such a simple thing. You just need a light bulb basically, so very cheap to build, and can actually tell you some decent information. So for example, if I plug this one in here, Switch this on. If I flick the switch on, nothing happens. The light bulb doesn't go on. And that tells me something straight away. It tells me that this power supply is not drawing any current from the mains, or if it is, it's so low that it's not turning the bulb on. And that tells me something. This here has probably got a primary side fault. It's probably had a primary side fault that was bad enough to blow the fuse, which is why this is not drawing any current at all. It could be that the primary side has an open circuit component, like a common mode choke or something like that. But usually it's an open circuit fuse because something else has failed. And yeah, the fuse could fail by itself if it was badly manufactured or got dropped or something, maybe. You know, it's a possibility, but probably more often than not, it's usually going to be a primary side issue that you've actually got a fault with it, and that's blown the fuse, and you straight away see, well, most likely there's a primary side issue. It's going to need probably new MOSFETs, maybe new driving chips, etc., etc. Could just be a shorted bridge rectifier or something that blew the fuse. That can happen. But I mean, you know, most of these new power supplies are all active PFC, and those circuits can sometimes go funny and blow up, so hey. But anyway, we straight away know this has got to be a primary side issue. So already I've kind of, well, we know the primary side has issues. It could have been caused by a secondary side fault. Unlikely though, because, you know, a dead short or something like that on the secondary, with a modern power supply like this, it'll just shut down. Generally won't actually blow up. Older supplies may blow up if there's a fault, like a shorted output thing on the secondary side, but these ones here is most likely primary side issue. Probably a blow-in PFC section, or could be bridge, but yeah. Anyway, so there's that one, for example. That does absolutely nothing. Now, we've narrowed that down. We can say it's a primary side fault. Take this other one here. This one, another power supply. It's on. We get a brief flash. Now that's pretty good. That's a fairly normal response. That's the current flow as the capacitor charges up, the main capacitor. You get a brief surge of current, the light bulb flashes briefly, and then it turns off. Now there's no current being drawn because the power supply isn't running, and the capacitor is now charged, so it's just sitting there charged doing nothing, so there's no more power. Switch this off, so we can take a look at this. So we know for a start the fuse has got to be good, bridge rectifier and all that's got to be good. It's good enough that it can charge the main filter capacitor. So we know that, you know, at least the input section of the primary side is probably fine. And the primary side obviously isn't dead shorted or anything, because otherwise this would have lit up full brightness, or the fuse would have already blown in this anyway. So that's good. That's what you want to see. You want to see a brief flash and then it should go off. What we don't know, however, is if there's actually anything coming out of this. So, you know, obviously you'd have to look at your 5 volt standby and see, is there 5 volt standby, is it stable, is it there, and then you can do a power up test and see if it actually works. And I can even do that as well. I can see I've got this little thing here. It's kind of like a breakout board thing you can use to do testing with. Well, we can see it's still got power, because even though that's been off, it's got there. So this pink one here is the 5 volt standby. I color coded the LEDs to the color of the wires, so it's a bit more easy to remember what it is. And then I've got these wires coming off to connect to a load if I want to load the rails up and give ripple tests and stuff like that. But red means we got PS on, and well, actually this is off, so I turn this back on again. You see that? May have seen that flash a little bit, because obviously the capacitor discharged a little. But we can see we got 5 volt standby here, and we got PS on, which is good. If I flick the switch here, PS on goes away because this switch is shorted it to ground. Nothing else happens. The fan doesn't spin, we get no output. So you can see this probably doesn't have a primary side issue, but it probably has like a secondary side controller issue or something. The fact that there's nothing on any of these other LEDs that don't even flicker, the fact that this didn't flicker, tells me that, yeah, it's not even trying to turn on. So probably it's like a, yeah, maybe secondary side controller or primary side controller fault. Something is not telling this to turn on, even though I'm switching it to do that. what should happen is all these other LEDs should come up, and this light should change to green, just to indicate that they've got power good signal once the rails are all correct. So yeah, for example, we can see what this primary side's probably fine, probably a secondary side issue with the controller. It's not even trying to power up at all. So that's a different thing. It's a different issue. So, well, of course, that's that's including this here, which again is just a bunch of LEDs. But we got one light bulb and a few LEDs. Quick diagnostic. I didn't even get a multimeter out. I didn't even turn on an oscilloscope. I just have a bunch of lights, and straight away it tells me something. Of course, this is only applicable to ATX power supplies, but you get the general idea. You can test standby rails on any power supply. We'll try powering it up and see what happens. And get the same thing. Take another one. It's this, another generic power supply. Do the same test. Let's see. What have we got? Put this on. Turn this on, we get a flash. So, again, we know the primary side is probably fine. Do we get anything out of here? I don't know. Let's get that out there. Well, we get nothing. So, we got a flash when I turned that on, but nothing coming out here. I can switch that. I mean, this is off now, but I can switch it on, tell it to power up, nothing happens. Well, we got no 5 volt standby anyway, so of course nothing's going to happen. But what does that tell us? Primary side seems to be okay, but we got no 5 volt standby. So, the 5 volt standby circuit is probably faulty. Or there's a short on 5 volt standby that means it's not running. If there was a short on the primary side of the 5 volt standby, the fuse probably would have blown already. Or the 5 volt standby could have blown without blowing the fuse, seeing it's a low power circuit. Maybe. But either way, we can say it's probably, the fault of this is going to be in the 5 volt standby circuitry somewhere, most likely. Oops, I seem to have cut myself. Anyway, but yeah, there we go. We got a diagnostic for this, rough diagnostic, pretty simple. And we got another one here. It's actually the same model as the previous one. But what's we got here? Flick the switch, nothing happens. So again, quite possibly, primary side has blown up and taken the fuse out. No point in plugging this in because you already know no light bulb here means this is probably dead. I mean, we could just for a laugh, but there's no point. So there we go. Nothing there. That's probably blown up primary side. I have another one. We have another one here. I don't know. Let's see. Got another flash. So there you go. This one does have a functioning primary side. And if we plug this in here, well, we get our 5 volt standby, we get our PS on. Let's see what happens if I try and power it up. Well, did you notice that? The light flickered. You might have even heard a relay click there, I'm not sure. But the light flickered there. What does that tell us? Well, you might think, oh, this has got some weird oscillation fault. Well, actually no. Most likely, this bulb here is not letting enough current through to actually run the supply. You can see it runs the 5 volt standby just fine because it's very low current, but trying to power everything up, we get this problem. So, you need to get a better light bulb. This is only 60 watts. We can do two things. We can get a larger light bulb, like 100 watt, or I can use the bypass switch. Because we already know, for example, the 5 volt standby is running. The 5 volt, the primary side is obviously not shorted. The light bulb didn't, didn't light up brightly, so we can use the bypass switch here, power it up. What do we get? Ah, interesting. Now I don't know if you can see these lights from there, but what happened when I did that? PS on went out, which makes sense because I've shorted it with the switch here to ground, which is how you turn these things on. I got a brief flicker of the fan. The fan briefly twitched. All the lights came on except for the orange one, which is the 3.3 volt standby. Sorry, main 3.3. There is no 3.3 volt standby. Well, except for the negative 5 volt, which doesn't exist on a modern power supply anyway. But we had yellow for positive 12, we had red for positive 5, we had blue for negative 12, we had no orange for 3.3. Now the power supply ran for a little bit and then shut off. That tells me primary side is fine, secondary side is mostly fine, the controller is fine because it's telling it to turn on, but the lack of voltage output on the 3.3 volt rail tells me the 3.3 volt rail is shorted, or there's something else wrong with it. Most likely it's shorted to ground, probably a shorted rectifier diode or something. This actually I think uses DC to DC converters in it, going by what I can see through the side. So I think with this one it's probably like a bad DC-DC converter module. I think a lot of modern power supplies now, they have like a single 12 volt rail, and then the 5 and the 3.3 are generated with buck regulators instead of from the main transformer, because it's a bit more efficient. So yeah, that tells me there's probably something wrong with that circuit, the DC-DC converter for the 3.3 volt rail, or there's a shorted rectifier diode or whatever. But yeah, primary side's fine. Something funny with the 3.3 volt rail. Again, I didn't have to do hardly anything. I just look at a bunch of lights. So simple. If you know what to look for. Anyway, let's try another one. I've got one more here. Now these ones are all ones that I bought. These 5 I just showed. Power supplies I bought a while back as faulty. Bought them for like a couple dollars each. Even if I can't fix them, they're good sources of fans and things like that. But this one here, for example, is one that I know, well, I have kind of an idea what's wrong with it. This is one that I've... what did I do? Oh yes, I got this given to me as faulty and I fixed it. Let's put this back here. But then it broke again. It worked for about a year and then it died again. Let me see, get this up around the right way. So turn this on, get a flash, we get our 5 volt standby. We know the thing, but I already know that the primary is fine on this. If I try and switch this on, I'll probably get the same issue. Well, no actually. Well, kind of. So the light lights brightly because it's pulling a lot of power. This thing runs a little bit, then turns off because it's running out of power, because it's not getting enough. But it's not doing the flickering that the other one was doing. But you know, that just depends on the style of circuitry, however they've implemented that. So again, I want to do the bypass for this. Switch it on, tell it to power up. We actually get all the rails. We get 12, we get 5, 3.3, and negative 12. This light's not green. There's no power good. So the supply is actually running, all the rails are there, but there's no power good signal. So this is something to do with the power good generation circuitry. PS on comes up, but yeah, everything else is fine, but there's no PS power good. Sorry, no power good signal, and that's on the grey wire. I just put that as red for PS on to say, well, if it's red it's in standby, if it's green it should be running and everything should be okay, even though those colours don't match up with the actual wires, even though everything else did. But I just did that because, yeah, it just made more sense. But all the other colours I tried to match with the actual standard colour coding for those rails. But yeah, so something wrong with the power good circuitry, and actually that's what was wrong with it when I got it. So I don't know what's happened, either that my fix has failed, what I repaired before has failed again, or some other fault. But yeah, so the supply seems to be working, but it's not generating the power good signal for some reason. That could be because one of the rails might be low or high, or there's too much ripple on one of them, or it could be that the monitoring circuitry is faulty and it doesn't realize that there's an issue. It doesn't realize that there is no issue. It thinks there's an issue and there's not, or something like that. So who knows? We'll see. I have to look at that into that. So I kind of guess what the problem with that is, but yeah. If I can just unplug this, that'd be great. Okay. So there we go. Dim bulb tester. Yeah. Kind of strange name, but hey, the light bulb should be dim if everything is going pretty well. And like I said, if it depending on how much power something like this runs, you need to get sometimes a high wattage bulb. In fact, I'm going to try that. Let's just try with a 100 watt bulb instead. So for example, take out the 60 watt, put on a 100 watt, actually do the same test and just see what happens. So switch this on, notice it actually flickered less. If I power this up, that's interesting. Yeah, okay, so it still is limiting the current too much. Interestingly, I saw the power good green light flicker momentarily. I don't know if you saw that. And then it went out again. So yeah, there's something funny with the monitoring circuitry in this, I suspect. Yeah, so I don't know, 100 watt didn't work for that, but maybe get 150 or even a 200. Yeah, anyway, but it all depends on what you're doing, what your supply is. You can adjust the values of the bulb accordingly. If you've got something where you really don't know the condition of it, you don't know what its normal operating current is, start with a low wattage and work up. Start with 40 watt, 60 watt, and then go up from there if you're not sure. In general, if the device is shorted, the light bulb will glow at full brightness. If the device is not getting enough power, but there's probably nothing wrong with it, the light may flicker, or like for example this one, it lights brightly when you power it up and then it goes a little bit dim and then the supply shuts down. Those are indications that there may not be a major fault, but it's just getting starved for current because the light bulb is too small. So yeah, it'd be interesting to try. I guess I don't actually have any higher wattage light bulbs than this is 100 watt. I don't have a 150 or 200. You can get them at specialist places, not generally at the supermarket, I don't think, unless there may be some, but yeah, you can find that online, I think, for things. But again, make sure it is a filament bulb. You don't want anything else that won't work. So if you want a really high wattage bulb, probably the easiest way would be to get maybe one of those work lights, the halogen work lights. You can do maybe 500 watt, 700 watt or something, if you really wanted a really high power one. But typically you wouldn't need something like that for even testing these. I think for this, maybe 150 or 200 would be good enough. But for just determining if there's a hard short, you can even just use any light bulb really. Well, the idea obviously you want to use as lowest as possible, like I said. Start with a 40 watt and just see what happens. But it's interesting. So yeah, bunch of power supplies, 6 different power supplies. All of them had different symptoms, and we can tell, like I said, just from using this light bulb here and obviously testing the voltages on the different rails. You could use a multimeter for that. You don't need to have a thing like this. You can have a quick look and see, get a basic idea of, before even opening the power supply, before even turning on any equipment. I've kind of narrowed down the rough area of where the fault is in each of these power supplies really simply and really quickly with stuff that's really cheap. So it's a good thing. It's a really useful little tool. It can prevent you from blowing up stuff if there's a hidden fault that you haven't been aware of, or if you've done work on it and you aren't sure if you've done the work correctly, or if you've made a mistake and you haven't realized. Or like myself in the other video, there's still a shorted component that you haven't noticed, like the bridge rectifier. And also, yeah, it works as a diagnostic tool, as I just displayed here. So yeah, it's quite a useful little thing, and like I said, it's very cheap to build. You just need a light bulb and stuff like that, and you don't need a fancy wooden box or anything, and switches and stuff. You can just literally have a couple of sockets and a light bulb. In fact, even the most basic way of using this would be just literally have a light socket on the end of a cord, and you can just solder that across the fuse holder in the power supply. Of course, that requires opening the power supply, so for something like this, that's not very useful. But yeah, that's one way of doing it. You replace the fuse with the light bulb and see what happens. I think that's an old trick they used to use in the TV servicing and stuff like that. There's one other thing worth mentioning with this. The light bulb does need to be, well, doesn't need to be, but best if you put the light bulb in series in line with the live connector, the line, the active. Obviously, generally, earth and neutral you just pass straight through from input to output. Active you break with the light bulb in series with that. The reason for that is it's possible, I mean, in general you could really, the light bulb it's in series, doesn't matter where it goes. You could put it in the neutral if you wanted, but that would be a bit silly. The reason for that maybe is because if you have a 3-wire device like this, it's got an earth. If there was a fault with the device where active was shorted to earth, and you had the light bulb in the neutral line, then it wouldn't do anything. You'd get a dead short from live to earth, and that would blow the fuse, or whatever, and the light bulb wouldn't even do anything because it's in the neutral, which is just off by itself doing nothing. So it's best to have it in the active wire, so that if the fault is going to earth or to neutral, it doesn't matter, it'll still current limit and alert you to any issues. Of course, you could also use a GFCI or a whatever, what's the other term? Ground fault circuit interrupter, and the other name for it is the what is the other name for it? Earth leakage detector, whatever. You could have one of these in series as well with it if you wanted to check for earth problems, and then the light bulb wouldn't matter where you put that, for example. RCD, I think, yeah. RCD, I think I think in Europe and stuff it's called an RCD, and in America it's a GFCI, I think. Anyway, but yeah, I mean, you could add that to this. I could add that to this. I mean, like I said, I've got a fuse, a switch. You could add all sorts of things. You add a voltmeter, current meter, not really necessary, but you could put them in. But at the heart of it, really, you just need a light bulb. That's all. Yeah, very simple. Very simple tool, but quite useful, as shown here. So yeah, if you haven't got one of these and you're interested in repairing stuff powered by mains, or even if not mains powered, you just want to have a current limiting device, you can use an old light bulb. Make sure it's an incandescent one. Make sure it has a filament. LED will not work. Not sure what will happen actually, but probably nothing good. Yeah, you could blow up the LED bulb or something, I don't know. Again, it's in series. Whatever you put here is in series, so the current that flows into this has to go through this. The circuitry in an LED bulb may not limit the current. It may just burn out or something. This might try and draw too much current through it because you don't have that, again, like I said, you don't have that positive temperature coefficient effect with the filament and the current limiting and all that. It only works with this kind of bulb. So yeah, anyway, hopefully that was useful. Hopefully that was interesting. Hopefully, if you wish to build one of these yourself, you will now have an idea of how to do so. It's pretty simple, like I said. You just pass through the earth, pass through the neutral, and put a light bulb in series with the active. there is pretty much nothing else to it. And like I said, you can add a fuse, safety features, whatever, if you want. Switch is always a good idea. Power LED, maybe, whatever. But yeah, it's pretty simple, but pretty damn useful, I think. Which is why I have one. And now I finally have one in a nice little box that looks good on camera. So there we go. Anyway, hopefully you enjoyed that. See you next time.